Hello everyone, this is Darren, and this is our lecture on outcomes. And we said at the very beginning that the bare minimum that we need to run a clinical trial is we need a problem, of course. We need some intervention that we hope solves that problem. We need patients enrolled in our trial, and an outcome that we're going to measure and use to judge the efficacy or effectiveness of the intervention. And so the outcomes is kind of the next step along that chain, and that's what we're going to talk about today. What things should we measure to help us understand whether the intervention works or not? And what we have is a balancing act, just like we had with the patients, where we're trying to balance internal versus external validity while controlling costs and everything else. Here we have the situation where we want to learn as much about the effects of the intervention on patient outcomes, because a clinical trial is a very involved process. And we want to learn as much as we can from the trial if we're going to go through the trouble of doing one. But at the same time, humans are really good at describing why patterns exist once they've seen them. It's very hard to predict what's going to happen in the future and then check that prediction against data. It's very easy to see data and then tell a story that makes a lot of sense based on what you've seen after the fact. The final thing is that not all outcomes are equally important, either from the clinical perspective, from the patient perspective. Sometimes those things are the same and sometimes they're not. So we have to think about outcomes in a relative way. So the first step to start balancing these issues is we generally in a clinical trial, we define different types of endpoints, and we'll touch back on this over and over again throughout the lecture. But generally speaking, we have what are called the primary endpoints, and those are the things that we judge the intervention as well as its safety. So these are the primary things that say, did we think this worked? Then we'll often have some set of secondary outcomes, and often it's just other effects you think are important clinically, but maybe not as important as the primary outcomes. And or it could be things that reflect the purported mechanism of the intervention. In other words, if you think that the mechanism of the intervention works through some particular biological pathway, then your secondary outcomes might be measurements of biological intermediates along that pathway. And so not only if you see the intervention works in terms of having an impact on outcomes, sometimes it doesn't matter how it works. If it works, then we're happy enough. But if you can also see evidence that it confirms the mechanism you thought it should work through, then that makes us feel even more confident about the intervention itself. And then there's this group of things, exploratory, which just becomes a catch-all for everything else. And I'll come back and talk about this at the end when we talk about core outcome sets. So we can rank the endpoints, but we have to think about what really makes an outcome useful on a more principled level. And so again, one, and this is kind of common sense, but it has to reflect the effect of the intervention. So that's a given. Two, and this is becoming more and more important, rightly so, it has to be something that's actually important for patients. Measuring a bunch of things that patients don't particularly value probably isn't the best approach. So more and more often patients are getting involved in trying to determine which outcomes we actually use in a clinical trial. Another one, and this one can be tricky too, is that you have to use outcomes that are convincing to decision. One of the things that makes a clinical trial or a test of an intervention different from other kind of areas of science is that at some point you'd like there to be a decision made about whether to actually use the intervention or not. People are either going to do this thing that you're suggesting based on this evidence and other related evidence or not. So there's a hard line decision. And you want to be convincing to decision makers. There's no point in running a trial if you're going to use outcomes and your colleagues, your clinical colleagues, are going to say, well, they didn't use an outcome that I find particularly convincing to make me think that the intervention actually works or is going to make a difference in my clinical practice. So you have to put a lot of thought into that. And finally, the thing that's most interesting, of course, to me, is that you want outcomes that have good statistical properties. And we're going to talk about this in terms of additivity, which we'll clarify, and then, of course, how it fits in with what we've talked about with noise and variance and power. So essentially, we want outcomes that lead to estimators that have low variability, which makes it easier to detect effects given a sample size. So the first challenge that comes up is this idea of multiplicity. And of course, there's an XKCD cartoon for everything, and one of the most famous ones, I think, is this one. And it really gets to exactly what the problem with multiplicity is, the idea that we have multiple outcomes that we're using to evaluate the effectiveness of an intervention. And so here we have, jelly beans cause acne, scientists go investigate, and they see that there's no statistically significant relationship between jelly bean consumption and acne. Then, after the fact, somebody comes in with the post hoc hypothesis that only a certain color causes it. And so what happens? They go through each of the different colors, and then right here, they find a link between green jelly beans and acne. Right? So we've got 1, 2, 3, 4, 5. We've got 4 columns here. So there's 20 different tests. One of those tests turned out to be significant at a level that we would normally use in a clinical trial. And you see right here, the reaction, of course, is whoa. And the next day, the newspaper. So if we think about our type 1 error rate, the false positive rate, that is a situation where we get a small p-value. That leads us to reject our null hypothesis, our null model of no effect. But sometimes we're going to do that incorrectly. In other words, sometimes we're going to reject the null when in fact the data were generated under a null model. In other words, there's no true effect of the drug. We just happened to see an extreme result due to sampling variability. And you can call that getting unlucky or whatever you want. That's going to happen sometime. And clearly, the more stabs at it you take, the more likely that any one of your attempts is going to hit that threshold of statistical significance wherever you set it at. So if I tell you that you're going to win a prize if you flip a coin and it's heads, well then obviously the more chances I give you to flip the coin, the probability of getting ahead increases substantially. And it's the same thing if we're looking at different endpoints in the trial. If I tell you that we're going to declare a success if I get a p-value less than 0.05, and then I keep on looking at different outcomes, and I get to declare success on the basis of any one of them being less than 0.05, then clearly there's going to be an increased chance of finding one false positive. And so we have to think about this in the context of regulatory agencies. Again, it comes down to decision making. There's either going to be an approval or not an approval at some point when a drug is developed and tested. And so regulatory agencies dictate strict type 1 error control, the false positive rate. They want that controlled. And so what exactly are we talking about? Now, they want the error rate controlled, the type 1 error rate controlled, that's alpha. But I said in the power lecture that all else being equal in a trial, once the trial's design is in place, right, the sample size is in place, the outcome and whatnot, I can do things to decrease the type 1 error probability, but that will necessarily result in an increase in the false negative probability. So you can think about this like a fire alarm that's going off in your house all the time and giving lots of false positives, right? That's a type 1 error. And you could pretend that there's a knob on your fire alarm. And let's say you could just turn down the sensitivity, right? You make it less reactive to particulate matter or smoke, whatever sets off a fire alarm. And that would reduce the number of false positives you get. It would make it harder for the fire alarm to go off. The problem there is that you would necessarily result in an increase in the probability of a false negative. By making the false positives more difficult, you make it easier to get a false negative. You make it easier to miss a fire when it really happens. Right? So we always have to think about that trade-off when we're thinking about ways to deal with this issue of multiplicity. Now, Stevenson goes through a number of options. I think he does a good job of explaining what they are and kind of the both sides of every consideration. And the things that come up the most, I think, would be these 4. So it could be that you just run one test. So out of all the outcomes you consider, you're going to say that the quote-unquote success of the trial rides on finding a small p-value on one particular outcome. And if you think about it, that really helps us start to kind of dive into this kind of unique situation when we're thinking about how we test interventions and make decisions to employ them or not. It's hard to believe that humans would make that kind of decision based on just one test on one outcome. Things are almost always more interesting and more complicated than that. The complete opposite of that would be that you just don't even worry about controlling type 1 error at all. You don't care about tests, but the key there is you just report everything. So if you do 20 outcomes and you do 20 tests on 20 outcomes, you calculate an exact p-value for each one of those, and you just report everything, and you let the reader make their own decisions about what they're going to do. Now, outside of the clinical trial environment, this is typically the approach I would take. In most of those instances, I'm using the p-value as a descriptive statistic about a parameter that I've estimated in data. I'm not necessarily doing an explicit hypothesis test. The idea of rejecting the null isn't as relevant outside of tests of experimental intervention. In the clinical trial, it's a little different, but the main reason it's different is because the regulators will not allow for this. You have to care about controlling the overall type 1 error, so you do have to do something about it. One of the more common things to do, and one of the easiest things to do, is to use what's called Bonferroni Correction. And all you do here is if you set, at the beginning of the trial, you set that your type 1 error rate would be 5%, alpha. You just divide it by the total number of tests. So if you do 10 outcomes, and you start off with alpha of 0.05, and you'll divide that by 10, and now your alpha will be 0.005. Now what that does is it controls what we call the Familywize error rate, which keeps the probability of making at least one type 1 error below 5%, or alpha, whatever you set alpha to, which is usually 5%. However, this is a really conservative correction because it really decreases the power. In other words, it increases the type 2 error rate, the false negative, for any given outcome you're looking at. It makes it harder to see effects when they're really there. And so some people balk at this conservativeness. More modern alternative that I've used and that other people are using more and more often is what's called controlling the false discovery rate. And it's easy enough. You get your student to apply a simple algorithm to do this. But what it does is if you think about all the null hypotheses you test, it keeps a proportion of those that are false positive below a certain level, 5% usually, the same as a type 1 error rate. What's important about this is that the correction scales itself appropriately to the number of hypotheses that you're testing. And so these are the kind of things that when you're at the beginning part of the trial design process, this is where you're working with your statistician to start to talk through, which of these options you think is the best. Is there some other thing? You'll see lots of stuff in the literature. You'll see lots of other approaches to this. Stuff I 100% don't recommend are what are often referred to as kind of hierarchical approaches, where you have kind of a gatekeeper outcome, and if it's significant, then you're allowed to test significance in other variables. None of that makes any sense to me whatsoever. I would usually tend to fall on one of these two options, either Bonferroni, which people understand and people tend to be quite comfortable with, but more often than not, I like this approach to controlling the false discovery rate. Now we have to talk about additivity, and this is really a statistical concern. We have a whole unit on this on linear models, but this is the basic functional form of a linear model, and linear models are what we use to test just about everything. And so what we have here is we have an outcome Y measured for individual I. So this could be Lisa's blood pressure. And from our entire data set, we're going to estimate the statistical model. And what it is, there's an average of the blood pressure, right, that describes everybody. There is some piece of other information, a predictor, X, and let's say that that's whether you're in the treatment or the control arm. So this value X can take on a value of 1 if you're in the treatment arm, or 0 if you're in the control arm. And so Lisa is either in the control arm or the active arm. So let's say she's in the active treatment arm. All right, so this is equal to 1. So then this beta that you estimate from your data, the computer does this for you using some of many algorithms. Beta then becomes the change from the mean blood pressure among people who are in the active intervention arm, right? It's beta times 1 for people in the intervention and beta times 0, so nothing for people who are in the control arm. Right? So beta is the average treatment effect of the intervention. And then we have some error, which is essentially the difference between a given individual's value and the mean of the outcome in the group they're in. And we use this model for lots of different outcomes, right? So we can use this for continuous outcomes. We can use this model with a little bit of tweaking for binary outcomes like alive or dead. We can use it for time to event outcomes. This is the basic functional form of a linear model. And the important assumption here is one that's called additivity. And it means that this beta in the model, how it's presented here, is constant for everyone. Right? We talked about the average treatment effect. We're assuming that the treatment effect is the same for everyone. That assumption is our best guess about how the intervention actually works. So it's an important thing to find a scale where effects are additive. One of the most important things to think about additivity is whether you think about the intervention working on the absolute scale or the relative scale. All right, so here this is an example from Stevenson. He's saying there's an effect of a bronchodilator on absolute and log FEV. And so when we do things, when we take the logs of things, then we're talking about relative effects, proportional effects. And so here we have a 15% increase. For this particular patient, we're saying that the truth without treatment that we can't see would have been 1,000. Their actual was 1,150, and so the difference there was 150. And this number is different, and the reason it's different is because it relies on their counterfactual value. So this, on the absolute scale, the effect of the intervention isn't constant. It's not additive. However, if we do the same thing, except now we're going to look at the log of FEV1, and we're going to add 0.14 here. This difference is 0.14. It's 0.14 for all of them. If you exponentiate 0.14, it's 1.15. In other words, 115%, a 15% increase. So here, by doing things on the relative scale, that restores additivity. That's what we're looking for. We're looking for effects that are constant. So here's another example where additivity becomes important, and this is the decision whether to use, so for example, a relative risk, or a risk difference, or an odds ratio. And so this plot shows the probability of some outcome occurring in a placebo group. So it's a hypothetical, could be 0, it could be all the way up to 0.8 to 1. The important thing to note is that everywhere in this plot, as the probability in the placebo group changes, that everything here is reflected by what's called a log odds of 1. We'll talk about this when we talk about logistic regression in a later unit, which gives a constant odds ratio of 2.7. And that 2.7, this odds ratio that describes the effect of the intervention, is constant regardless of what the probability of the outcome in the placebo group is. However, for the other two things, either the difference in probability, the risk difference, or the increase in the relative risk, which is this line, you can see those things change dramatically as the probability in the placebo group changes. So if you were doing a trial and as it happened the event was fairly rare in your placebo group, we think about if you had a group that was not intervened on, your population, your natural population, and the probability of this event occurring was 0.2, then for this effect of the drug, it would be just here around 0.23, would be if you were on a risk difference, or overall the relative risk would be something like 2. All right, so here, this is the example Stephen gives us. When you maximize the risk difference, it happens at probability in the placebo group of 0.378. The risk difference here is 0.245. The relative risk here would be 1.64, an increase of 0.64. But the odds ratio is still 2.7. The log odds is still 1. Out here to 0.8, even though it's the same effect of the intervention on the log odds scale in terms of odds ratios, now what you've got here is the relative risk, has plummeted because the risk is already so high. Right? So this is just another example where we're talking about we want effects that are additive. And one way we often get that with binary data is by modeling things on the log odds scale. We'll talk about this a lot more in the unit on linear models. You just need to know this is what we're talking about when we talk about additivity. All right, so here we're going to use survival modeling. We're trying to model the time to some event occurring. And let's say that we have 2 different trials, and we're trying to judge the effectiveness of the intervention in one of 2 ways. We can either talk about the absolute risk reduction, and if you take the inverse of that, you get the number needed to treat, and people really like to talk about effects of intervention in those terms. Or we could talk about the improvement in median survival. I think most people, if you just ask them, would think both of those things are important. How much do we reduce the absolute risk? And then can we improve median survival time? And so consider these two interventions, intervention 1 and intervention 2, trial B, trial A. And then here we have two groups. There's a group who received placebo and a group who received a new treatment. And at any given time point, here, time, we can calculate this length between these things. And so here, looking at these two trials, for trial A, you'd say the effect of the drug, the absolute risk reduction was 3.7%, less than the absolute risk reduction in this trial is 14.9%, right? So you'd say this drug works better. It has a greater risk reduction at this time point than this drug does. Importantly, the functional form of these trajectories is the same, and they all reflect a hazard ratio of 0.6. So we use hazard ratios when we do time to event. Again, we'll talk about this in the nonlinear models, but the point here is that we have a constancy of effect on the hazard ratio scale. If we go to looking at median improvement, though, in other words, if we look at the time where both of the placebo and treatment arms cross the median survival time, that would be indicated by this difference. This is an improvement. These people, the median survival here is longer. It comes out to 1 point something compared to this group. However, for this other group, the one that had the poorer absolute risk reduction at a given time point, their median survival improvement is in 5 years. So by this scale, you'd certainly conclude that this drug being tested in trial A was the better drug. Again, the take-home message here is that when we're using outcomes that are based on absolute differences, then the degree of difference we detect is going to be strongly related to the baseline risk. However, when we use relative effect measures, then we can get to some number that reflects the treatment effect that's constant across levels of initial baseline risk. And that's what odds ratios give us, and that's what hazard ratios give us, even though they're not always easy to interpret in some kind of a immediately intuitive way. And that's often what log transformations give us for continuous variables, this ability to describe constant additive effects. Now, we touched on this when we talked about generalizability, when we talked about patience, and this balancing of internal versus external validity. And so we can always, if we have an idea that a particular feature or characteristic of patients, or maybe it's of clinicians or clinics or hospitals or whatever, if we think that there's something that predicts a differential effect of the intervention, in other words, if we think there are two groups in which the intervention will operate differently and have a different effect, we can build that into the linear model. And so here we would introduce another variable A, and people would take some value for that. And then it would have an effect on the outcome, which would be reflected by this beta coefficient that we estimate from the data. And so now your particular value for the outcome is the overall mean in your sample plus some effect based on this variable plus some effect based on this variable. And then we would just have a third variable in which we just multiply these two things we think are interacting. We just multiply them and create a whole new variable and an estimated coefficient for that. And this gives us the departure from the main effect that's driven by being in one of these groups. This gives us an interaction effect. So we can always test for that kind of heterogeneity in that way. The problem is to get precise estimates of interactions requires lots more sample size than we need to estimate these main effects. So to really get a handle on whether that interaction is there or not, we need a lot more patients in the trial, which is often not feasible. That's why this doesn't happen. All right, another big thing to talk about that people do often that people need to stop doing most of the time is unnecessarily categorizing variables. And so we hear the justification for this a lot, that people like kind of thresholds because they tend to be clinically interpretable. There's this idea that decisions, you're making decisions in a clinic, and so you want to know if something is above this, then I'm going to do something different than if it was below. The problem from a statistical point of view is it always leads to information loss. So when I have a continuous thing like this measured on the number line, right, I can go in this example minus 10 all the way up to positive 10. There's lots of different information here. First, I have the rank I could rank people according to this. But beyond that, I get actual distance. In other words, I know the distance between 0 and 1. That's the same as between 1 and 2, and that's the same as between 2 and 3. All of this is information, right? And when I do a categorization, I lose most of that information. In other words, if I take people who naturally fall somewhere along this line in a continuous way, and I divide them into the reds and the blues, well then someone who's here compared to someone here, I'm going to treat them exactly the same as comparing this person to this person. I've lost a remarkable amount of information about the actual distance between these observations on this number line, and that has real consequences for the power of the trial. And so imagine we have a situation here where we have two distributions of some continuous outcome in two groups, active and control. Right? So I have this red group here, and somewhat confusingly, their mean, I've used a blue line here to reflect the mean of the red group. Right? And a red line here to reflect the mean of the blue group. Right? But obviously the mean here is kind of the bulk, the highest point of these peaks. Right? So you can see that there's a difference here. Right? There's a difference in the mean between these two groups. This in the active has shifted. If we think about the control as the distribution that we would expect to see our outcome in like just an untreated population of patients, then we will look at our active group that's shifted a little bit to the left. In other words, the outcome's a little bit lower in these people. All right. So let's say we do a power calculation. So these data were generated in a way so we have an effect size here of minus 0.5. In other words, we shifted to the left the distribution. People in the intervention arm, their values were lower on average than people in the control arm. And this was somewhere we used just a simple t-test. We'll talk about t-tests more. We set our alpha to 0.05, and we assume there's equal variances in the two groups. What we plot here is power as a function of sample size, so we get a power curve. So in other words, we've set all the other things about our study in stone, and now we're going to consider the trade-off between sample size and power. And so power is terrible to detect this effect of minus 0.5 if I have nobody in the study, and then power quickly goes up as I add sample size. In other words, as I move to the right across the x-axis, then power starts to rapidly increase. Right? And here, this is my sample size that I would need in each group to hit a power of 0.8, 80%, or a type 2 error rate of 20%, right? And so that's just around 60. Or I could get up to a power of 0.9. You know, it's still under less than 100 in each group, right? So this can help me plan my study. So given an effect size in a test and a certain type 1 error rate, then I can do a trade-off between the sample size and the power to detect that effect with this test. Right, this is what would happen for the continuous case. Now, let's go back to those two distributions. And let's say that we define a case where the cutoff is 10%, the top 10% in the control condition. In other words, I'm going to say that we're going to call people diseased if they're above this line. And you remember the space here, this would be equal to 10% of this overall curve. Right, so that I'm going to use that to make some kind of a cut point here. And then as it turns out, if we just focus on the active arm distribution, that reflects 3.8% of the patients. So now what I'm saying, instead of saying that there's a minus 0.5 shift in the mean of this distribution, I'm doing another statistical test that says that the prevalence of an outcome is 10% in the control, and I want to test to see if it's 3.8% in the active arm. That's how I'm describing improvement now. No longer a mean change, but a difference in proportions of people who fall above this line. Right, so I've switched. What happens to power then? Well, now, to detect that same effect, but now reflected categorically instead of continuously, you see a much shallower curve. So here, before, I was just around 60 to get 80% power, 60 people in each group to get 80% power, and now at the same sample size, I don't even have 30% power. In fact, now I've got to get all the way up to 250 people, 500 total patients, where before it was 120, to detect this effect. So when people start to talk to you about, well, we need to categorize this outcome, this is why the statistician will almost always advise against it. Because each one of these, you're talking extra patients put at risk, extra patients sacrificing autonomy and choice of treatment, when you could have just done the same study and kept your variable on the continuous scale, detected the exact same effect, for a third or fewer of the sample. Now, that's the most compelling reason that often these categorizations don't have any basis in biology. For example, I was recently doing some work and people like finding these cutoffs in different measures. In this particular example, it was skeletal muscle area index among cancer patients and trying to predict survival. And you can do these things that are called optimal cut point analysis, and they'll find the cut point in a continuous thing that will maximize your ability to predict people's survival. Right, so you can do that. And so this analysis we did, and it came out very clear, for example, for the males, that there was in fact a best cut point around 56 centimeters squared over meters squared. Right, so a cut point here existed, and there's a lot of papers who go on to then look at how people are either have low or high values for this thing, skeletal muscle area index, as a predictor. However, when you actually model these things continuously, right, so this is modeling thing on the log relative hazard scale. In other words, higher is riskier, lower is less risky for survival. You can see if you had a true categorical effect, then it would be flat, and then at that cut point it would drop to some level and then be flat again. It would be a step function. If it were really, the effect really was categorical. But instead we get this kind of smooth curve where the risk comes up and the risk goes down, and lots of noise in this measurement too. Right? So the categorization, I can get a method to tell me the best cut point, but it doesn't mean that the cut point makes sense or is a useful thing to do. And then we have this other issue, and this is the thing that I think probably irritates Stephen Sin the most, is this idea that we have responders. So for example, instead of just measuring diastolic blood pressure, we might say that a response is if the diastolic blood pressure drops by 10%, or if diastolic blood pressure goes from greater than or equal to 95 millimeters mercury to less than 90. And so then you would have these kind of weird situations where this kind of a drop, a 9.9% drop, would not be counted as a response, whereas this 5.3% response would be. And it's kind of silly ideas with this concept of who's responding. It's an unnecessary categorization of a continuous thing. And so it comes with all of these consequences that people don't really understand or think through. And of course, we talked about this idea of response. There is no response in a clinical trial because there's no counterfactual for each individual person. So I put this in a blog post that I had up for last week, where the authors are looking at this group. This is each dot is a person in the active arm of a trial. And some people, if we measured their insulin at the start of the study and then at the end, some people went up, but some people went down. The point here isn't that they changed. People change all the time. It's that what would their value have been if they had been in the other arm? Maybe this person would have still been this high. Maybe this person would have still been this low, right? We talked about that. There's a natural progression of disease. Things are going to go up and down whether you treat them or not. And so the key here is that we compare a summary of what happened to all of these people in the active group to the placebo group. But that information isn't reported here. Well, the main change is 0.72, but maybe the control group went down 0.72. We can claim there's no effect of the intervention. But people take this as some kind of an indicator that individual response can be observed in a trial, and it can't. And another nice just like illustration of this is imagine that we have this counterfactual experiment, and each one of these sets of 2 points here, the blue and the red, is one person, right? And it gives us the difference between what we would see. If we could see the counterfactuals, this would be their value if they were given blue, and this is their value if given red. This is their value if they're in the placebo group. This is their value if they're in the active control group. And you can see for every single person in this hypothetical world here that the red being treated will increase in the outcome value, right? So the counterfactual here, which we can never directly observe, is that the red is better for everybody, not even on average, for everybody. However, in a real clinical trial, we obviously don't see both red and blue. We can only see one for each patient. And so that's what it looks like, right? So here, some people are lower, some people are higher. But we know in this, again, this like hypothetical world we've created, we know that the effect of the intervention was constant and the same for everybody. And that's what we're trying to infer from this information overall by taking the mean in the two groups. So that's response. So that we don't just needlessly categorize people as responders because it's a categorization, because it results in a loss of power. It's just generally a bad idea. Okay, so the next topic then is this idea of surrogate outcomes. And so a lot of times you think of the clinical thing you want to use to demonstrate the efficacy or effectiveness of the intervention and say something like death. The problem is that you have to often, for some interventions and disease areas, you'd have to wait a long time to actually see an impact on death for your intervention if there was one. And trials cost lots of money. Patients are sacrificing time and effort. So studies with long follow-up present a real challenge to the degree where it can start to threaten the internal validity of the trial. So if you're getting people who are dropping out, we're losing track of patients, we can't follow everybody up. Well, the people who drop out of a trial tend to be different from the people who stay in. And so now what you're starting to do is you can only look at the effects of the intervention of the people who stayed in, and you might be introducing some biases there. You might have other situations where you have outcomes that have better statistical properties. In other words, that the estimators for those outcomes are less variable. So it requires fewer patients to see the effect of the intervention. It might be less expensive to collect some particular types of information than others. So essentially a surrogate is when you're using another outcome as a stand-in for the one you'd really like to use from a clinical perspective. The issue here, though, is that people often don't put too much thought into how they use surrogate outcomes. And we have to go into the world of causal inference to really think about what makes for a good surrogate. And we have to think causally, not just kind of statistically or clinically. And a good surrogate, a perfect surrogate, in fact, would be reflected in this situation where we have randomization to intervention X. And then we really want to know how it affects Y, but Y is very hard to measure, happens a long time into the future or whatever. And so what we do is we use some surrogate S. And a surrogate isn't just something that's related to Y or correlated with Y. It's something that fits along this causal structure. In other words, it's something that completely mediates in this particular DAG. It completely mediates the effect of Y on X. In other words, there's no other way for the intervention to affect Y except through affecting S. Now that would be a perfect surrogate. And in this case, if you knew this was true, then you would use this with no problem. This would become your primary endpoint. And if you saw a relationship here, an association here between randomized allocation and this particular endpoint, you'd be really happy to conclude that your intervention is going to affect Y. The problem here is that we can never know that this is actually the causal structure. We have to reason about these things. And there's lots of threats to this, very reasonable things that can make this a less than perfect surrogate. So for example, it could be that Y has lots of other causes. And so you might see a strong effect on S. S might have an impact on Y, but it might not really describe much of the variation in Y overall. So your effect here, which might be quite strong, this overall relationship could be quite weak. Right, so you might be seeing a strong effect on your surrogate and maybe not that much effect in the thing you're really, really interested in. We have other situations where you're trying to reason about these things, and you're trying to reason about the strength of the relationship between S and Y, your surrogate, and the outcome. But those two things could be confounded, just like we've talked about in the DAGS lecture. So just because we see a relationship between these two things, it doesn't mean that this relationship is necessarily causal. If we're using other information from other studies to justify our surrogate. That stuff usually comes from observational information, which the threat of confounding is always there. Right, so understanding this thing is necessary for understanding overall the value of the surrogate, but this is always going to be somewhat questionable. We could also have situations where you have, again, this effect of X on Y. You have one pathway that's mediated by S, but you could have other pathways right, that you're not thinking of, where X could be affecting Y through other intermediates. And you can even have situations where this can be a positive, right? So X can have a positive effect on S. S could have a positive effect on Y. But you could also have a whole other pathway where X and Y, actually there's a negative relationship. In other words, giving someone the intervention lowers this through this pathway, even though through this pathway it increases it. And if all you're focusing on is here, this relationship between X and the surrogate, then you're going to get the wrong answer. So the key thing to take away here is that surrogates have to really be carefully thought through from a causal inference perspective. And some of your reading deals with this issue. Surrogates have become a way to observe the effects of interventions. And it's really important because time and time again we see examples where an intervention very clearly seems to impact a surrogate, but later evidence that's able to actually look at the hard clinical input finds that there's no effect on, say, survival or the clinical outcomes that you're really interested in. And so you need to be really cautious when you're using surrogate outcomes. All right, so what else can we do if we don't do a surrogate outcome? Let's say we're still interested in something like death, and we still have trade-offs. It doesn't mean you should never use a surrogate. In your discussion this week, I want people to try to find examples of useful surrogates. Other things you could do is to use a composite endpoint. And so sometimes you just don't have enough power. You'll never get enough patients enrolled in your study to look at the effect of a treatment on death is a really common example. And so what do? So what happens then is you take several outcomes and then you just combine them, right? And so then the outcome becomes if any of these things happened, then we count you as a yes, you experience the outcome. If none of these things happen, then no. And the key consideration here when you're doing composite endpoints is it requires a lot of thought, again, about the individual outcomes that go into the composite. And you should always describe what goes into the composite outcome. You should always provide analyses of each individual outcome, even though they're not well powered. You should still have a look at the data in that way. And you have to really think about the relative importance of the things that go into the composite. Because if you have a composite with like cardiovascular death and rehospitalization, but most of the people who get counted as experiencing an endpoint were due to rehospitalization, then what are you really saying? Right, so this requires, there's not a black and white thing here. You can use a composite, but you have to think about the stuff that's going into it and what it really means. And usually what it means, the implication is that you're saying that everything that goes into the composite is kind of weighted equally, either by clinicians or by patients or anybody else. You're treating them all the same by lumping them all together. And this leads us kind of the final point of the lecture, which is this issue of outcome switching. And this is a really big topic and something you have to proceed with a lot of caution. One of the things that happens in clinical trial world that doesn't happen in a lot of other areas of science is the idea of registration. And this is generally, I think, is an extremely good idea. And so whenever you run a clinical trial now, you're obligated to register certain information about the trial's design before you recruit patients. And this includes the outcomes. So the outcomes would be one of the things that would go in your clinical trial registry. And again, that has to be on an approved registry before you recruit a single. And what can happen, though, is that we know, and we'll talk about this next year when we start to talk about adaptive trials, but we know that you plan a trial at the beginning, things change, and sometimes recruitment lags. In fact, usually recruitment lags. And so sometimes what you have is a situation where you anticipate problems with recruitment and that you have a plan in your trial protocol to switch out endpoints if that happens. So you might start the trial looking at one particular endpoint, a hard clinical endpoint, for example, but then have it in your protocol that if your recruitment is going, so and so slow, that you'll switch endpoints to something that you'll have more power to actually consider. So even though when these are planned like that, they don't inspire a lot of faith. And because there's this long history of what used to happen before trial registration came on board, and what still happens in lots of areas of science, and still happens in trials too, is this situation where this line here, year 2000, is when everything people were required to register their primary outcomes on clinicaltrials.gov. And so these are the results of these different tests, right? So a positive here means that there was a risk reduction in the primary outcome. Positive means there was a benefit to this particular intervention. And so these are the distribution here over time of trials that either found a benefit, a null result, or harm. And you can see that most of the trials here before the trial registry, which dictates that you say what your primary outcome is, and that's what we're talking about here, the relative risk of the primary outcome, you can see that most of them are positive or null and none of them are harmful. Then all of a sudden this comes in, this one change, and then what happens? All of a sudden these trials are reporting null effects, even one with harm. This is a remarkable result. There's no other explanation other than the fact that in this particular year, people had to start registering their trials on clinicaltrials.gov, in particular nominating what their primary outcome was. So prior to this point, clearly people were being very willy-nilly, and they were looking at the data and they were analyzing it, and then they were saying what their primary outcome was based on the results they obtained, which is bad. Right, so this is why people are very suspicious of any outcome switching whatsoever. And one of the more famous examples happened this last year in a trial called Ischemia. And essentially it was a very large trial, it was supposed to be a very large trial, and it was looking at the value of stenting in high-risk patients but that had stable ischemic heart disease. And people weren't sure. There's supposedly equipoise on whether stenting is actually useful or not. Lots of people think it's very useful. Lots of people suspect it isn't. And so they planned a study. They were going to recruit 8,000 people, and they were based on this composite endpoint. And so the composite was made up of two really hard clinical endpoints. So it was either cardiovascular death, you died from a cardiovascular cause, or you had a heart attack, myocardial infarction, right? So two very serious things. If you experience either one of those things in this trial, then you were going to be classified as someone who experienced the endpoint. The problem is that they under-recruited. And when they hit about 5,000, they added 2 soft endpoints to the composite. So this was rehospitalization for unstable angina or heart failure, right? So much softer endpoints. The fact that you've been hospitalized, is obviously not as clinically important as dying or having an actual heart attack. And the problem was, when they made this change, they went on to the trial registry and changed it. And people noticed it. And people then started talking about it and made a big deal of it. And as it turned out, the change was built into the original trial protocol. So in other words, it was built into the protocol from before patient recruitment started, but that wasn't shared and communicated appropriately until it got changed on the registry after patient recruitment had started. In fact, over 5,000 patients have been recruited. So the appearance was not good. The appearance was like people were outcome switching, and people really threw a big fit about this. It was a really big deal in the cardiovascular research community. And so now what you have is a situation where the study's results, a very expensive NIH publicly funded big trial, has been completely thrown into question. If people came to this study at the start and they were in favor of stenting, then they're still going to stent. And if people came to this trial, clinicians came into this trial and read it after all the fuss about it, and they didn't believe stenting was useful, then they're not going to stent. And one of the interesting things here, also from an equipoise perspective, was why they under-recruited. And they under-recruited, one of the reasons was that some of the clinicians, it's a large multi-center trial, some of the centers were not randomizing their patients. In other words, clearly those people who were participating, those clinicians who were participating in the trial, didn't have any faith that there was equipoise and weren't willing to randomize patients to either get stented or not on the flip of a coin. And so then the trial under-recruited and required this change in endpoint. So it's a really interesting kind of example of how all this stuff kind of matches together. I'm going to make one more point about quality, that when people run trials, what happens is, or any other study, they often tend to kind of just do things their own way. And outcomes are no different. the researchers involved in that particular study, they sit in a room and they decide what outcomes they're going to use. And the problem is, if everybody uses slightly different outcomes, then when it comes time to kind of synthesize evidence across all of these studies, then we can't synthesize evidence if people aren't making like-for-like comparisons. And this becomes particularly important for secondary outcomes. Oftentimes, the primary outcomes, you think about those are the things that you want to make sure you power your trial to detect the appropriate sized effect in. In other words, you set the sample size to make sure that if there's an effect of your intervention on the primary outcomes, you're able to detect it. And then the secondary outcomes, you don't consider them at all when you're considering your sample size. And so then it's really important for those outcomes that you're able to consider evidence from multiple sources. In other words, you use multiple trials to get the sample size up for those particular outcomes to say something useful about them. All right, so the key thing here is that now what we have is there's something called core outcome sets and the Komet initiative. And so when you are planning your trial, what would be a good idea is when you're starting to think about, you've thought about the problem you want to work on, you've thought about the intervention, and now you're starting to think about outcomes. You can come here to the initiative. You can search the database down here and say you can come up with, you want to look at a standard set of patient-centered outcomes for lung cancer. So you're doing a lung cancer trial, and you want to think about the things that you should consider in your trial that'll be the same things that other people consider in their related trials, right? So you can just search forward, and they'll tell you through. And not only just that, it's not just the outcomes, but they'll also give you stuff like case mix variables. So what other demographic, clinical, and tumor characteristics should you measure, right? So those are the things that help us understand like the level of baseline risk that the patients are at. So it's just about getting everybody on the same page when they're doing outcomes, so that when it comes time to chuck everything into a meta-analysis, we can actually do one that gives us useful, valuable answers. All right, so that's it for outcomes. You've got the reading. As always, if you've got questions about the reading, you've got questions about anything on this lecture, please just go ahead and put a question on the Unit 4 Q&A. If you don't want to put a question there, you could always email me directly. It's no problem, and I can put the question up anonymously. And if someone is particularly stuck on something, get in touch. We can always arrange a video conference or whatever. All right, thank you very much. Bye.